Welcome to part 5 of my playlist about the best strategies for alkylating alcohols. This presentation is about the reductive alkylation of alcohols with aldehydes or ketones. This reaction does not proceed as smoothly as the reductive alkylation of amines because acetals are more difficult to reduce than imines or iminium salts. Acetals or hemiacetals cannot usually be reduced directly, but must first be converted into a cationic intermediate by an acid. Thus, only reducing agents compatible with at least slightly acidic conditions can be used to reduce these oxocarbenium cations. Silanes and hydrogen in combination with catalysts and acids are, for instance, well suited for the reduction of acetals or hemiacetals. Alternatively, alcohols can be converted into enol ethers by treatment with aldehydes or ketones, or by addition to alkynes. Enol ethers can be hydrogenated, but not as readily as simple alkenes. The choice of catalyst, solvent and additives is a bit more tricky, and the literature should be checked for optimized conditions. I'll show you an example later. Even carboxylic esters or mixtures of alcohols and carboxylic acids can be reduced to ethers, often under conditions similar to those of the reduction of acetals. When acidic conditions are required for one of these reductive alkylations, one potential side reaction is the formation of symmetric ethers. Moreover, the electrophile can be reduced to a primary alcohol, and under forcing conditions, some alcohols and ethers can be reduced to alkanes. This is an example of the conversion of a primary alcohol into a cyclohexyl ether, a reaction that cannot be readily accomplished by alkoxide alkylation with a cyclohexyl halide. Here, triethylsilane and a catalytic amount of triflic acid were used to achieve a reductive alkylation of the alcohol with cyclohexanone. No hydrogenation of the terminal alkene occurred, but the yield of ether was only 51%. A higher yield of ether was obtained in this example, where isopropanol was alkylated with a substituted acetophenone. The reducing agent was hydrogen, and to prevent a benzylic CO bond cleavage, a rather unreactive copper-based catalyst was used. In this optimized example, a secondary alcohol, protected as silyl ether, was alkylated by treatment with a slight excess of propanal. Triethylsilane was again the reducing agent, and a catalytic amount of bismuth tribromide was used as acid. The target ether was obtained in a high yield after only 30 minutes at 30 degrees Celsius, without any alkylation of the sulfonamide or debenzylation of the carboxylate. This is an example of the conversion of a carboxylic acid into an ether by treatment with an excess of butanol. The reduction was effected by hydrogen in the presence of a soluble ruthenium catalyst and 10% of an imide. Because of the high stability of carboxylic acids and esters, a high reaction temperature and hydrogen pressure were required. The antiviral agent oseltamivir, sold under the brand name Tamiflu, contains a bis secondary ether that is difficult to prepare by the conventional Williamson synthesis. A convenient strategy, however, is the reductive cleavage of an acetal, as shown here. Despite other reducible functional groups, such as the alpha-beta unsaturated ester, an allylic CO bond, or the mesylate, treatment with a triethylsilane and titanium tetrachloride at -36 degrees Celsius cleanly yielded the target 3-pentyl ether in high yield. The final epoxide was obtained by intramolecular mesylate displacement with aqueous sodium bicarbonate in ethanol. As mentioned in the first video of this playlist, substituted ethylene glycols are more acidic than simple alkanols and can therefore be alkylated in protic solvents without the use of strong bases. This is an example of the formation of vinyl ethers by addition of alcohols to acetylene and their catalytic hydrogenation. Both reactions gave high yields and are an inexpensive, environmentally friendly way to convert alcohols into ethyl ethers. Here are some more examples, which you can also find in the description of this video. I've also included some oxidative strategies, in which alkanes or arenes are converted into ethers by treatment with an alcohol and an oxidant. Hope you found this useful, and stay tuned for some more presentations about practical organic synthesis.